So today's the second lesson on chapter 11. This is the last chapter. Okay, we are going to study series. Now, what do you mean series? We already learned, discussed sequences. Okay, let's begin with the following problem. We already talked about this before, I want to add them together like 1 plus r squared and r cubed. And yeah, so first of all, what does it mean? This means you're going to add infinite many terms. Okay, so this should be viewed as the limit as n approaches infinity of the n plus 1 term, the sum of n plus 1 term. Okay, right, so you get n approaches infinity. If this sum approaches a number, then that limit is going to be called the sum of this infinite sum, the sum of infinite many terms. Okay, so we know that we have the following fact. Okay, the fact that says the limit of n approaches infinity r to the n is going to be 0 if the absolute value r is less than 1. Okay, because 2n's power is r times r times r is getting smaller and smaller and smaller. Okay, so this is it's if r is positive between 0 and 1, then r to the n is getting smaller and smaller. It approaches 0. Now, using this fact, maybe we can find the limit. Okay, so we assume that so this is going to be equal to, right? It's 1 minus r to the n plus 1 over 1 minus r. So you can combine into just one fraction. Then it's clear that if r is less than 1, absolute, then this is going to be the limit is going to be this. Okay, if r is going to be absolute value r is less than 1. Okay. Right, so this is a special case is like that 1 plus 1 over 2, 1 over 2 square, 1 over 2 cube, and just keep going. And then this is supposed to be, if I is 1/2, right? So that's answer is 2. Okay? We also have 1 plus 1 over 10, 1 over 10 square, 1 over 10 cube, okay? Now, infinite terms, this really means 1 plus 0.1 plus 0.001 plus 0.00, no, sorry, I'm missing a term. It's going to be make sure my battery is okay. I just got a new battery. Haven't put it back yet. All right, so 0.001 and keep it going. So this also can be written in the form 1.11111. Okay, this is also written in elementary middle school, right? In this is notation, when it's repeated. So now, using advanced mathematics, let's understand what's the meaning of 1.111 when it's repeating. Okay, this is viewed as the limit of this the sum of those terms. Okay, so by definition, this should be viewed as limit, okay, of the nth term. So the nth term, right? It's 1 plus 1 over 10, and all the way to 1 over 10 to the nth power. So we got the limit, okay? And let me redo the problem, okay? So it's going to be 1 minus 1 over 10 plus 1. Here's 1 over 10, okay? And then that term is going to be 0. So that term approaches 0, 1 over 10 to the n plus 1. So the answer will be, is going to be 1 minus 0, 1 over 10. So what do we get here is 9 over 10, so it's going to be 10 over 9. Okay, so it's going to be 10 over 9. It's larger than 1, of course, but you can express as a fraction, okay, 10 over 9. Okay, this is a series, okay? We're going to study more general series instead of just this one. So if we have, yeah, let's do some exercise first before we study general series. And let's look at examples in the book. So here's the problem, number 22. Let's concede 5 over pi to the n. Right, so we are going to have infinitely many terms. So this is a view that it's going to be like a 5 pi over pi and 5 pi over pi square and 5 pi cube and cube. Okay. So the sum of the infinite term. Now this is viewed as the limit, okay, of the sum of n terms, or n plus 1 terms. So you can do like this. What's going on here? Okay, this is going to be, you take pi over 5 over pi out. Then the first term will be 1. Second term 1 over pi. The third term 1 over pi square. Right? Yeah, just like the usual way we do. So now here I is going to be 1 over pi, which is smaller than 1, right? So this is according to the above formula, it's going to be 1 over 1 minus sum. Okay. 1 over 1 minus sum. So it is going to be 5 pi minus 1, okay, over pi minus 1 if we multiply the sum. Okay, so this is the sum. It's convergent, and it is going to be 5 pi minus 1. Okay. Now, I mentioned that when I look at the factor, right, r to the n, right? R to the n, what happens if r is greater than, absolute r greater than or equal to 1? What happens about limit r to the n? That's only, most of the time it's divergent, okay? This can be viewed, yeah, that's many cases here. If r is greater than 1, then this will be positive infinity, okay? Because like a 2 squared, 2 cubed, 2, right? If r is equal to 1, this is always equal 1, right? If r is, right now we assume r is, it's absolute r is greater than 1, so r equals -1, the limit does not exist because it's always jump from negative to positive 1. I think, yeah, doesn't matter. It's r is less than or equal to -1, that's fine. So either it's always between negative and positive, or between negative, it's getting, the absolute value is getting larger, but the sign always alternating. Okay, so the limit doesn't exist. Okay. So in this case, 1 plus r squared all the way to r to the n is going to be right still like this. And then this does not approach to any number. because this r to the n plus 1, okay? So we have a problem here. If of course, r cannot be 1, otherwise it's even not defined, okay? So this is true only if r is not equal to 1, otherwise you cannot write it in this form, okay? This does not approach any number. Okay, it's divergent, okay? In other words, infinite term this is divergent. Okay, it's not convergent, means divergent. Okay. Now we can also written in the form is sigma notation form. Okay, this is we'll talk about this later. Let's look at the example first. Okay, this next problem, problem number 24, and then I'm also doing number 26. Okay. All right, so this notation means when n equals 1, that is going to be when n equals 0 to 3, and the denominator is just 1, okay? The next term is when n equals 1, it's going to be 3 squared, and that's 2, okay? And plus 3 cubed, and that's going to be 2 squared, and minus 3 to the 4th power, 2 cubed, and keep going, okay? So many terms here. So how do we analyze that? Okay, we can take the common fact out. Okay, the term we want to take it out is, I think, 3. 3. Okay, so this is going to be 3. Then you get 1 over 1 minus 1 over 3 over 2 plus 3 square over 2 square minus 3 cube over 2 cube, and keep going, right? So this is actually is going to be 3 1 plus r square r cube, and so on. Here r is going to be negative 3 over 2. Okay. Now clearly this is a divergent. Okay, since I is the absolute value I is going to be 3 over 2 is greater than 1. Right? It's clearly it's time. If you really want to see it, you look at the first n plus 1 term. The first n plus 1 terms is going to be you will get the 1 minus r to the n minus 1. You can see that the limit doesn't exist. Okay. The next question is problem number 26. Okay. Now let's start using sigma notation. Okay, this notation, okay, let's deal with it. So remember, let's say assume k start from 0 to n, okay, and r to the power k. This notation is just 1 plus r squared all the way to r to the n, okay? Yeah, just list of them. K equals 0, you get 1, k equals 1, you get r, k equals 2, you get r squared. And this is this can be combined into that form. Okay. So now how do we use this to if you take the limit, okay, and this notation, okay, really means the limit as n approaches infinity of this sum. Okay. Yeah. So this is going to be the limit n approaches infinity, 1 minus r. Okay. and this is going to be just 1 minus 1 over 1 minus that if ever pseudo is less than 1. Okay. Yeah. So this notation n equals 1 to infinity really means the limit. Okay. So now, yeah, let's look at. I'm going to use k. Let's k start from 1 to n. Okay. So 3 to the n, 6 to the 2n minus 1. Okay. You can actually combine them into one fraction for this particular problem. We can do like this, step by step. 2 to the 2n minus 1 is 2 to the 2n divided by 2, right? So it's going to be 6 divided by 2 is going to be 3. Let's use a k here. Let's k, okay? So that's going to be 3. Then you can also continue to simplify. It's going to be 3 to the k minus 1. Okay? Now what? You can the first leading term, if you want to see it, it's going to be 2 square and 1. Okay, the second term will be 2 to the 4th power and 3, and keep going, right? The last term is 2 to the 2n, 3n minus 1. Okay, so can we combine them into one fraction? I think the answer is yes. Okay, we can actually, you can rewrite this. It's like a 4 over 1 and the 4 square over 3. And here's 4 to the power n to the 3n minus 1. So you can take 4 out. That's all you need. Okay? Equal 1 plus 4 over 3. Here's 4 to the n minus 1 over 3 to the n minus 1, right? Yeah. Then you can apply the formula, about formula. It is going to be 1 minus 4 over 3 to the n, because here's n minus 1, and 1 over 4 over 3. So you can actually find the sum of that. Okay, it's going to be, if you simplify that, it's going to be negative. So the denominator gets negative 1/3. So you can put the negative 12, 1 minus 4 over 3 to the n. Okay, now clearly, this one approaches infinity. You can see that it's negative 12 plus 12 times 4 over 3 to the nth power. And then 4 over 3 is getting larger and larger. This goes across to infinity as n goes to infinity. Okay? So what does that mean? That means it's not only that divergent, it's divergent to the infinity. Okay? So my conclusion is, let's assume let's k equals 1, right? And this is going to be 6 2 to the 2n minus 1, 3 to the n. It's going to be positive infinity. Okay, it approaches infinity, positive infinity. Okay. Now, if I change the problem a little, 2 to the k minus 1, that'll be a different story. Okay, so if I change it to 6, yes, 2 to the k minus 1, 3 to the k, then it's convergent. Okay, and you can get the answer. Let's do it directly. How about this? I remember this is what we have, right? start from 0, r to the n, that's going to be 1 to 1, right? If I is less than 1, okay? So I'm trying to change this into this sum, infinite sum, into that form. So, but the k starts from 1. So I can let n equals k minus 1. How about like that? When k equals 1, n equals 0. Okay? So this is going to be n start from 0. And when k is infinity, infinity minus 1 is still infinity, 6. And here k is 3 to the k is equal n minus 1. And here k minus is just 2 to the n. Okay? We change the index. Okay? So now I take 6 here, 3, 2, 3 to the power n. Okay? So I'm trying to rewrite in the form like above. So that will be 2. Take a 2 out. Okay? Now it's exactly the same form. All right? N start from 0. So then you will get 2 over 3 here. It's 1/3. Denominator is 1/3, and turn this upside down, it gets 2 times 3, so 6. So the limit is 6. Okay? Yeah, let's talk about the general one. Okay? So you are given sequence. Okay? N start from capital N to infinity. Okay? So given a sequence. Okay? It's not necessary from 1 or from 0. Okay? By definition, here's definition. This notation n of n is going to be the limit. I'm going to use m. Okay, m approaching infinity. Here, n from capital N and a. Okay, just the finite sum. Okay, in other words, you have a to the capital n plus 1, and a m. So you have the sum of so many terms. Then let m go to infinity. That's a notation. Okay. So the sigma from n equals capital N to infinity means the limit of this partial sums. All right. And when the limit exists, then we say it's convergent. Otherwise, we say it's divergent. Right. And the most interesting example we already discussed, it's called geometric sequences. And we know when it's convergent, when it's divergent. Okay. Okay, so let's look at the problem. Consider, yes, let's study this here. The sum of this infinite term. Okay, this is if you write down the detail, it's going to be 1 over 1 times 2, and 2 times 1, 1 over 2 times 3, 1 over 3 times 4. Okay. All right. So you have infinite terms, but is it convergent or not? Okay. So this is going to be the limit. Let's say k approaches infinity. Let's use a k. No, that's just notation. Okay. And the trick is, yeah, I have to write this, right? I have to make sure this one is convergent. Okay. So this, according to the definition, yeah. If we expand it, the last term will be k and the k plus 1, right? Can I group them into one fraction? We can. So what do we do that in order to group them into one fraction, we have to decompose it into two fractions for each term. It's 1 over 1 minus 1 over 2. And here's 1 over 2 minus 1 over 3. And keep it going, 1 over 3 minus 1 over 4. And so many terms, 1 over 2 minus 1 over 2 plus 1. Okay? Then, there's plus between all between them. Then you look at those, they're all canceled out in the middle. Okay? So what is left is just 1 over 1 minus 1 over k plus 1. Great. Then it's easy to see it approaches 1 as k approaches infinity. Okay? So my answer is it's going to be what? Yeah. So it's interesting to see that it's going to be what? Now another example is from the math competition for the kids in the middle school. Okay, I just saw the problem. This is a very interesting question. Is you have a square, you need a square. Yeah, end up with this sequence. Okay, you have a square, you put a larger circle there, right? This is unit square. There are many problems like that, and then you put a tiny circle here. Then you put a tiny circle here. So there are infinitely many circles. And what is the total area of all these circles? Okay, I describe it. Then you actually have to use this geometric series idea. Okay, that's why it's coming. Why it's called a geometric series, not coming from geometry. Okay, from the problems. So what they do is unit circle. So this is radius 1, that's a radius 2, right? And so on. So you have to zoom in to find the relationship of two circles. This just zoom in, okay? And then here's a tiny bit of circle here. So this is this is a R circle. This is R plus 1 circle. Okay? I want to find the relationship between them, how they're faster decays. Okay? How that fast decays is you can see that this side this is going to be square root 2 RK, right? Square root 2 RK. This can be viewed as the sum of RK. Oh, I don't know what's going on here. Okay, so I can view this the sum of these two. Okay, and plus this part. There's 3 parts here. So you will get RK plus RK plus 1 and plus the square root 2 RK plus 1. So you will get, if you move that, square root 2 minus 1 R to the K, and actually square root 2 plus 1 R to the K plus 1. So the relationship is so the radius decays, but it's given by this formula. Okay, for the simplicity, so the square, at least the square, even faster. Okay, so R to the K plus 1 square, because we're talking about the area, right? So the area is going to be pi square root 2 minus 1 square root 2 minus plus 1 square. Don't put a pi here right now. Just look at, so it's R to the K square. So the square of the radius is decayed in this way. Okay, And this term, for the simplicity, I can assume, let's call it A, okay? Just some number smaller than 1. It's a fixed, okay? So, so now what happens? You have R1 equals 1/2, right? That's the first one. That's from the unit square. Then R2 square is going to be A R1 square, right? And then R3 square equals A R2 square, then A square R1 square. So finally, you get R to the K plus 1 square equals A to the K R1 square, right? So now the sum of the whole area, okay, is going to be sigma, the total area, is going to be sigma K start from 1 and pi R K square, okay? Right? And add them together, take a limit. So this, according to, because this is going to be AK and R1 square is just 1/4. So I'm going to put here is a quarter, and since RK is actually A to the K minus 1, okay? And yeah, when K equals 0, you know, A is going to be square, like 2 minus 1 square, 2 plus 1, that's square, which is less than 1, okay? It's a very strange number. So now you will get, take a pi over 4 out, you get, what do you get? You get 1 plus A square, and that's get geometry series, okay? So that's going to be pi over 4 is 1 over 1 minus A, okay? So it is interesting to see that the total area of those circles is given by this formula. Okay, so this is where you get the geometric series, right? Right. Another. Let me give you another. Yeah. Sometimes not always end up with geometric series. How about like this? N equals 1. Right? Is it divergent or convergent? Right? Now you can write down, okay, all the terms. You can look at the case term, okay, and from 1 to the K. Right, so get partial sums, right? So what you get is when N equals 1, you get square 2 minus square 1, right? Then plus when N equals 2, square 3 minus square 2. And then N equals 3 is going to be square 4 minus square 3. And keep going. The last term is N equals that. But you can, what you can see is square 2, or they all cancelled out. Then the square 3 cancelled out. So how many terms is left? I think it's only 2 terms left, which is the last square 2 minus square 1. Right? All the term will be cancelled out. And clearly this approaches positive infinity as K approaches infinity. So you can see that it's divergent. Okay? Okay, so it is divergent, and then you can also say I can put a positive infinity. Okay. All right, so given a sequence, and this is a this is a, remember, this is a viewed as limit of this partial sum. So I'm going to denote the partial sum by SK. So you will get another sequence. You will get another sequence. Okay. So if this sequence convergent, then you say the series is convergent. Is there a difference between sequence series? Sequence, you just say sequence of number. Series is going to be the limit of the partial sum. So this is called partial sum. Is called partial sum. Right. All right. It's interesting to see that the partial sum n plus n, okay, n, the difference of those two partial sum is going to give you the nth term. How do you see that? Well, partial sum is going to be like a n plus a n plus 1 and so on, right? A n minus a n plus 1 and so on, a n minus 1, right? So there, so the common term will be cancelled out. Right? The common term will be cancelled out. Right, that's good. This is a nice identity. All right, so now we assume that if the partial sum is convergent to L, a finite number. Okay, then you can see that the nth term approaches 0. Right? Then the limit of the nth term is going to be limit of the first partial sum and this, right? So this is going to be L minus L is going to be 0. So if the series is, in other words, if the series is convergent, the nth term approaches 0. Okay, but conversely, it's not necessary to be true. Okay, so we have to be very logical. Okay, so this is a way, mathematics is very precisely. You can, when you argue with someone, if that is true, then you can but converse is not necessarily true. Okay, so I want to, so here the theorem said that if this series is convergent, okay, then the limit of the nth term is 0. But conversely, it's not true. Okay, the converse might not be true. I should even. So this is just the necessary condition for the convergence of the series. But this is our first theorem in this chapter to tell whether the series is convergent or not. You can use that to prove, only to prove a series is divergent. You cannot use that to prove the series is convergent. Why? Because the converse is not true in general. Okay, it's not guaranteed. So when you look at the statement, make sure they are both equivalent or not, right? Like in geometry, what is a complete statement of Pythagorean theory? Many students will tell me, if it is right triangle, then a squared plus b squared equals c squared. That's just a part of the statement. The statement says that a triangle is a right triangle if only if a squared plus b squared equals c squared. So in other words, if you're given 3 sides of right triangle, and if you check a squared plus b squared equals c squared, automatically, it guarantees this is right triangle. Okay, so that's a back forward. Yeah, but some statement is just stated the necessary, like this one. If it's convergent, then the nth term convergent to 0. And conversely, it's not true. Okay, so but this is already powerful enough to check something is convergent. Okay, is divergent. So, for example, yeah, for example, this sequence, this series, okay? This series is okay, the nth term is going to be n minus 1 over n plus 1. And this clearly approaches 1 as n approaches infinity, right? So that means it is 1, but not going to be 0, right? It's not going to be 0, therefore, the series is divergent. The sequence. The sequence is convergent, but the series, okay? This implies the series is divergent, right? Is divergent, right? Why? You see, imagine, you add a term, infinite many term, but each term is almost going to be 1, right? So definitely it's getting larger and larger the numbers, the sum. Like that every day you get $1, right? Suppose you live forever, almost $1, maybe 98 cents, but never smaller than that number, right? After 1 billion years, you get $1 billion. It almost, so it's getting large. You cannot, it's not going to be convergent. It's divergent, right? Yeah, mathematics, it's interesting. If you carefully do some computations, like a compound interest, something like that, you will learn how to invest the money someday. Okay? It's always keep saying that how much money you're making is not that essential make you rich. Right? You have to learn how to invest the money, how to save money during a certain period of time. Then that gives you, 10 years later, the two guys make the same amount of salary. They have the same, I should say, same background, financial background. Then one guy never cook, always eat outside. Other guy trying to save money, only spend $150 for food every month. Then you save another, some money. Then imagine how to save. Then at the end, and find a way to invest. 10 years later, you can see the bigger difference. Okay, so yeah, and the majority of people just they don't save money. I think according to statistics, more than 50% of people have less than $1,000 in savings account. Yeah, you can randomly check. Yeah, but that's a statistic. I don't know whether it's fake or not. But this is we have to learn how to save. Okay, so I just say do some computations sometimes, and for your financial plan. All right, so let's do the next problem. Okay, so here's next problem. This is a okay. So number 30, for example. K squared over k squared minus 2k plus 5. Now this is a pretty complicated sequence, series, right? So when k equals 1, 2, you can write down all the terms. The question is whether it's convergent or not. Okay? And first of all, you look at, sometimes the question is that if it's convergent, can you find the sum? Can you find the sum, right? But first of all, you make sure it's convergent. So how to see whether it's convergent? There are many ways to check whether it's convergent. we're going to learn many ideas. But the first idea we learned is, you know, if it's geometric series, maybe I can easily check whether it's convergent. But the only way so far, we only learned the theorem to check divergence or not. Okay, if it's divergent or not. So let's look at this term. Okay, the case term is k squared minus 2k plus 5. I think it's obvious it does not approach 0 when k approaches infinity, because when you divide by k squared, you get this, and clearly it approaches 1. As k approaches infinity, it's not going to be 0. So therefore, the series is divergent. You have to say the series, okay? Because AK is convergent. The case term is convergent to 1, but the series is divergent. Okay, and you can say that mentioned by the theorem for divergence or by the nth term test. So there are some names, nth term and test. Okay, we can call the nth term test. Okay. Here's another one. Whoa, this is a little simple, right? All right, so this series is also divergent. The reason is the nth term, 3 to the n, 2 to the n plus 3 to the n. If you simplify, it's going to be 2 over 3 here is n and plus 1. Divide the numerator and denominator by 3 to the n. Then clearly it approaches 0 plus 1 over 0 plus 1, so which is 1, which is not going to be 0 as n approaches infinity, right? So it is divergent. How about this? Now, in order to solve this problem, we have to mention the theorem. We know that if sigma, if this and both are convergent, right? Then Bn plus Cn, add them together, is convergent. Not only convergent, the limit is going to be the sum of those two limits, okay? And it's like a usual sum. Right, just add them. You can separate, and the proof is just use a partial sum, take a limit, okay? So this is as long as both are convergent, then A is corresponding in terms, you form a new series, the new series is convergent too. And not only that, the sum is going to be, the infinite sum is going to be the sum of those two infinite sums, right? So now, in our case here, okay, you actually have a two series. 2 to the n, 3 to the n, here 4 to the n, right? And this is going to be 2 to the 4 and plus 3 to the 4 to the power n, right? So now let's focus on each of them. Okay. So that is going to be, yeah, you can separate them. So as long as both of them convergent, then implies the original series is convergent. And we know this is convergent to geometric series. It's 2 over 4 is less than 1, 3 over 4 is less than 1. And since it started from 1, so our answer will be, if you take this out, it will be 1 over 1 over 4. And you can simplify to 1 half, okay? Here, 3 over 4, 1 over 3 over 4. So you can simplify it. You get 1 half. 1 half, this is over 1 half, it's 1 actually, right? And here you get 3 over 4 and the 1/4, so it's 3. It's going to be x going to 4, the final answers. Oops. Okay, our next question is, how about that? Yeah, think about it, okay? Is it convergent or divergent? So I send an email to everybody in this class. I say, well, take it serious. I did not see, I only see about 2/3, sometimes when half of the students come to the classroom. I make sure, you read the book. If you're not attending the classes, make sure you read the books. If sometimes like today, I'm okay, figured out how to record it, then I can post it, okay? And watch the video. That helps you to understand the material, okay? It's actually save your time, yeah. Then do your best, because you will see that it's involved more deep mathematics to study these problems. It's not like, give me a formula, use a substitute, figure out something, and integrate the integrals. Okay, that's why that's the reason why it's pretty challenging. Okay, you do need a deep understanding of mathematics to solve this type of problems, like this one. Right, I give you a series. Right, my question is whether it's convergent or divergent. If it's convergent, can you find the sum, right? That's always a question. Okay, if it's divergent, give me the proof, right? I have to give a proof, argument. So you always, acting like a lawyer in the court. If you don't give a good proof, you cannot prove this guy's innocent or this guy's guilty. Okay, so you're acting like a lawyer. You have to quote the laws, according to which, right? Yeah, provide the evidence and then a court. Yeah, yeah. So. Yeah, I had a student actually he's a lawyer. He's a 45 years old. He came asking why he's taking classes. He already have a nice job. Like, he said, well, he's taking math courses, chemistry, biology, because he already forgot lots of things about chemistry. So if you deal with some cases, like a chemistry, right? You need the knowledge in this area too. Otherwise, you have to deal with very narrow cases. Okay. All right, so now this is a question. Okay, natural log of n over n plus 1, right? This is a n. Okay, question number 1 is n is n converging to 0 or not, right? And we look at that. N equals natural log of n over n plus 1. That's going to be natural log of 1 over 1 plus 1 over n. This approaches natural log of 1, which is 0. Oops. All right. So you cannot use this to prove the series is convergent or divergent. Okay. It'd be useless information as long as it's 0. Okay. You cannot say the series is convergent. You can only say the nth term is convergent. Okay. So yes, you are getting each time you're getting a smaller and smaller term. But still, because you have infinite many terms, you add up all the terms, you still get the infinite sum. Okay, so not useful information. Okay, I cannot say this series is convergent. So how about the difference? So let's look at the partial sum. Right. So you're going to get natural log of 1 over 2, natural log of 2 over 3, natural log of 3 over 4, and so on. Natural log of n over n plus 1. Right? Can you see that this is convergent? Right? Or divergent? It's a sum of natural logs. So of course this is going to be product of those terms. Right? Yeah, this type of mathematics, if the student is actually win the math competition in the middle school, they usually have no trouble to understand the material easily. Oh, I know this technique. Okay, so it's called math counts. Have you heard about math counts for middle school kids? Yeah. Okay. So add them together, then you simplify, right? They all cancel out. What you get is 1 over n plus 1. So when n is getting larger, the 1 over n plus 1 is getting small. This approaches negative infinity as n approaches it. So it is divergent, right? Because the partial sum approaches negative infinity. Okay, so this series is going to be the limit of n approaching infinity Sn, which is going to be negative, divergent. Yeah, sometimes, yeah, in the generalized sense, it has a limit. The limit is negative infinity. Sometimes it does not have a limit. It's alternate. The limit even does not exist. But here, in the generalized sense, it's the limit still exists, but just negative infinity. But we can say this is divergent. So this is a good example to show you the converse of in the theorem, right? The nth term test. The converse is not necessarily true. Right? When we say a series is convergent, then the nth term convergent to 0. But conversely, if nth term convergent to 0 is convergent to 0, then the series is not necessarily convergent. And this is a good example. Right? This is a good example. Right? Another example, we cannot prove it right now, but we do it later, such as like that. Right? This is divergent. Okay? This is divergent. But the limit of the nth term is 0 still. Okay? We cannot prove it until in next section. Yeah, the next section we're going to study that. Okay, we're going to prove that. Yeah. In section 11.3. But this is another example show you the series is divergent, but the nth term is still convergent. So when you check the nth term is convergent, does not convergent to 0, does not mean this series is convergent. Right. Next question is. Let's see. Determine the value of x for which the series is convergent. All right. Clearly, when x equals 0, it's divergent, right? But this is geometric series, so you can express it in the form 2 over x to the power n, right? We know that when it's convergent, it is convergent if and only if 2 over x is less than r, right? So it is convergent if and only if that's sufficient necessary condition. 2 over x is less than. Right? Then from here you can solve this inequality. Right? The inequality, this is the same as absolute x is greater than 2. X cannot be 0, of course. Okay. About another problem. All right. Now this is a challenge. This is difficult problem. Question. Determine whether this series is convergent. All right. If it is convergent, can you find the sum? Find the limit. Can you see that? The nth term converging to 0. But still, I said that cannot guarantee its convergence. If you want to prove its convergence, you have to prove it direct, right? I cannot prove its divergent because how do you prove its divergent, right? So we have to look at the partial sum. Let's say partial sum SK. Right? Can I group them in together? Okay, it's 2 square minus 1, 2 3 square minus 1, right? And there are so many terms, k square minus 1. I'm tutoring a 4th grade chart, and he can do this problem. I guarantee. It's very surprised. He's a genius guy. Yeah, they always have like every year they find a one. So this is yeah, he's different from other kids. He never touched the iPad. When his mom gave her buy the nice book, he will be crazy. Just sit there and just want to read the math book. Okay. Yeah, addicted to mathematics. I should have said that. But the majority of the kids just cannot get rid of the iPhone and the iPad. So you are going to have face a very challenging problem. When you have a kid, you are busy. How do you deal with them? You know, you buy an iPad or iPhone to them, and that just wastes a lot of time. Okay, and this is yeah. If you know how to handle this, then your kids will do well. All right. All right. So we can. The idea is very simple. Okay. 2 over n squared minus 1 is equal to 2 n minus 1. Whenever you see n squared minus 1 squared, is n plus 1. Okay. Then I can decompose it. It is going to be, you know, do you remember the fact, right? The integral techniques, right? They're called decomposition. Partial fraction sums, right? Partial fractions. So we already put the 2 there, so you don't even modify it. It's going to be n plus 1 minus n minus 1. It's 2. The numerator is 2. So that's good. So using this, then the SK is going to be, right? It's going to be 2 minus 1, 2 minus 1, right? Minus 2 plus 1. That's the first term. And plus 3 minus 1 minus 3 plus 1. Okay? And 4 minus 1 minus 4 plus 1. And just keep it going. K minus 1 minus K plus 1. I hope I can see lots of terms canceled out. Okay? So yes, they're canceled out, but they cancel in the following way. This cancels with that. Okay, be careful, right? And one of us, you see, there are terms not just next to each other. You know, you have to write down more terms so you can figure out what terms will be left. Okay, right? So like 1/3 minus 1. Are we good? Yeah, let's write more terms. Otherwise, it's harder to see which term will be gone. Okay, and that's be 5 minus 1 minus 5 plus 1 and plus 6 minus 1 minus 6 plus 1. And then should be enough. Then I have to take k minus 1 to minus 2. And k minus plus 1 is k. The next term will be k minus 1 minus k plus 1. Okay? So if it's harder to see like that, then I group all the sum, then group all the positive term or all the negative terms. So the positive term will be 1/2 minus 1. So even you can write down, just expand it to 1/1 plus 1/2 plus 1/3, right? And all the way to the 1/k minus 1, right? Then that will be much easier. And here minus, and minus is going to be 1/3, begin with 1/3, 1/4, 1/5, and 1/k plus 1. Then it's easy to see what terms will be gone, right? So you start from here and to here, this part will be gone. And here you have a 1/k is left, right? So you will get 1 plus 1/2 minus 1/k plus 1/k plus 1. So all the term in between them is good. Okay. Yeah. So now it's clear that it approaches 3/2 as k approaches infinity. Okay, and then okay, we find the sum. Okay, so I can write down this n squared n star from 1. It's going to be 3/2. Got it?